Okay, we're gonna go through some examples. We're gonna talk about Newton's law of gravitation today. So I want to make sure you have time to work on the assignment on schools. You can hopefully finish it today. So I'm gonna go through some of these, like bell ringer. Go through pretty quickly here. This is again just Kepler's third law: p squared equals r cubed. So in this scenario, we know the period is 8.8 years. So I'm trying to find r. So again, what I prefer to do is just go ahead and symbolically get r by itself first. So take the cube root of both sides, and you have r equals, like we've done several times, this would be p to the 2/3 power. So the distance away from the sun is going to be 8.8 to the 2/3 power. And then just put that into your calculator. We're going to use your calculator a lot today, so if you don't have it out, you may want to get it out because the numbers we're putting in are pretty big. 8.8 to the 2/3 power gives me approximately 4.3. Because this is R, this is AU, so 4.3 AU. So this would be a planet. If a planet had a period of 8.8 years, so it took 8.8 years to go around the sun one time, its distance would be about 4.3 AU, which is about 4.3 times further away from the sun than Earth is. Which again, that at least makes a common sense check, because if the period's longer, we know it has to be further away. Okay, so excuse me. We previously talked about Kepler had established that the planets moved around in ellipses. But again, if you were to ask Johannes Kepler, say, okay, well, why did they do that? There would be no answer. You don't know. Basically, it's sort of working backwards. This is what a lot of times people do. It's almost like guess and check, right? Where you put in an answer and you see if it works out. And if it doesn't, you manipulate your answer until you get what matches your observations. Well, that's what Kepler did, right? He matched his observations, right? He developed a model that matches his observations, rather than having a model that predicted observations, so to speak. So he didn't know why. But Isaac Newton, don't have a lot of time, unfortunately, to talk about Isaac Newton. We've talked about him before a little bit when we talked about Newton's laws. But just genius is an understatement. I mean, he's just a once in a, not even a century probably, once in a century, once in a couple centuries level of genius. Pretty impressive guy. I recently found out, I knew that, if you don't know, it's sort of disputed between him and another mathematician named Leibniz who developed calculus, and some people think they both developed it independently. Regardless, Isaac Newton is credited with developing calculus, and supposedly he developed it during there was a virus, a disease going around, and they had to quarantine. So he in quarantine developed calculus, which is pretty impressive stuff. Anyways, one of the things that Newton came up with is his law of gravity. So there's obviously this apocryphal story about Isaac Newton, sitting under a tree, and an apple falls on his head, and then he thinks of gravity. But it's not exactly. Everybody knew that stuff fell to the ground, right? No one was surprised that stuff fell to the ground. But if you were to ask why stuff fell to the ground, again, you wouldn't have a good answer. Aristotle had come up with a theory that things on Earth just fell in straight lines down to the ground, but there was no real reason why. Isaac Newton is the first person to put into words what's going on. So, at its core, gravity is simply the attraction that mass has to other mass. So stuff is attracted together, stuff that has mass. But this force is very weak. Okay, when we think of gravity, we probably think of gravity like it's a force that's strong or whatever, but it's actually an incredibly weak force. It's the weakest of the four forces that we know of, if you look at them in direct magnitude. But gravity works over long distances, and gravity becomes noticeable when you have something that's very large, right? So think about the Earth, right? The Earth is huge. All of its mass, right? All of the mass that makes up Earth, every bit is pulling right now on, for example, I have a calculator on my desk. It's pulling on this calculator. This entire object, right? Earth is bigger than you can ever see. You can spend your whole lifetime trying to see all of Earth, and that's just the surface. You're not going to see all the surface. And there's so much more to Earth inside. The point is the Earth is unimaginably big, and all of Earth is pulling down the calculator, and then I can just pick it up like it's nothing. I just overcame all of Earth's gravity working on this calculator by picking it up. Even something relatively heavy, people can pick up, right? We're able to overcome the entire Earth's gravity simply with our human muscles. Gravity is incredibly weak, even on a big scale, but it does work over larger distances better than other fundamental forces. So what you see here, this equation, this is Newton's law of gravitation. And so obviously you've got this PowerPoint, your access to this PowerPoint. We're going to use this equation several times, so you'll need to have this. You have here Fg, this is the force of gravity, is going to be equal to this big G. This is called the universal gravitational constant. It's just a number. It's a number that what these constants do is they work with the units. They make sure that all the units work out, and they also make sure the units work together in creating this force. So the constant here, it's important that you have it, but it has no effect. It doesn't change the units. It makes sure everything works out. So you'll have newtons over here because it's a force, and newtons over here because it's a force at the end of it. But anyway, so you have big G is the gravitational constant. M is the mass. M2 is the second mass, right? Because again, it's the force between two masses. So you're going to have both of those masses on top, and then divided by the distance squared. R is the distance between the two. Now this is important when we have large objects. We are going to use a model where we're assuming that object is being represented by some infinitely small point with that mass, right? So you're going to see this in one of the problems when we talk about Earth, right? All of Earth is pulling on you. The way that we'll do this calculation is we're going to assume Earth is one infinitely small point with the mass of Earth, and if you're standing on the surface, right, you're the whatever the radius of the Earth is, that's how far you are away from Earth, so to speak. And I think you'll see that. Okay, so one more time. F is your force of gravity. This is going to be measured in newtons. G is this constant, 6.67 times 10 to the negative 11. Again, you can ignore this stuff here. This is just the units. I mean, I wouldn't say ignore it, but you don't have to do any, you don't have to square anything or divide anything. It's just units right here. M is the mass of the first object. M2 is the mass of the second object, and divided by the distance squared. Okay, so you can see some units there, and you can see that the units will work out to be the same at the end of this. All right, let's look at a practice problem together. We'll do this one together. It says, let me pull it up over here. A woman has a mass of 60 kilograms and is standing on the surface of Earth. The Earth has a radius of 6,371,000 meters and a mass of 5.972 times 10 to the 24th kilograms. Find the gravitational force between the woman and Earth. All right. So what you need to know is that, some of these numbers, they'll be big numbers, right? It might look a little ugly, but your final answer shouldn't be too bad. It's just going to be, putting it all into the equation. So let's look at this. So I'm going to start by writing my equation, rewriting. Force of gravity is going to be equal to G times M1 times M2 divided by R squared. Okay, so this is going to be G is 6.67 times 10 to the negative 11th, I think. Let me double check that. Let me go back. 6.67 times 10 to the negative 11, yeah. So I'm just going to write that up here. Well, I'll just write here. So G is 6.67 times 10 to the negative 11. Okay, there's G. Times the first mass is the woman. And it doesn't matter M1, M2, because it doesn't matter what order you multiply those in. It doesn't matter which one's M1, and it doesn't matter which one's M2. So times 60 times the mass of the Earth is 5.972 times 10 to the 24th. Okay, I'm running out of room already. That's not good. Times 10 to the 24th. Divided by the distance is 6.371 times 10 to the 6th. That's just that number in scientific notation. is that distance squared. Okay, so again, there's a lot of stuff to put in your calculator here, but it is just calculator work at this point. I'm going to do the top. So I'm typing in my calculator 6.67 times 10 to the negative 11 times 60 times 5.972 times 10 to the 24th. Okay, so on top, it'd be better if I had this in, I'll just put in scientific notation. I have 2. Okay, just making sure I didn't type in anything incorrectly because it was smaller than I expected, which is, oh, yep, and I did type something incorrectly. I put 4 instead of 24, which would be a pretty big difference. Okay, there we go. I knew the number on top I should get is pretty big. Okay, so I get on top 2. Again, don't worry about rounding too much. 2.39 times 10 to the 16th. On bottom, if I square this number, it's 6.371 times 10 to the 6th. Be careful when you square this in your calculator. Just be sure that you are, I would write it just like I have here, put in parentheses 6.371 times 10 to the 6th, close parentheses squared. So on the bottom, I get 4. We'll just call 4.06 times 10 to the 13th. And then be very careful when you divide these. I'm going to say exactly what I'm typing into my calculator. So I'm putting in open parentheses 2.39 times 10 to the 16th, close parentheses, divided by open parentheses 4.06 times 10 to the 13th, close parentheses. Okay, so all that, and my final answer here is 588.7 newtons. Again, don't worry about rounding too much, but hopefully you're getting around 589, 590, somewhere around there. So that's the gravitational force. I want to point out real fast, for all objects on Earth, right, on Earth's surface, right, we can make an approximation. And these things right here, if let's say M1 is the Earth's mass, again, then all of these things right here, right, for all objects on Earth's surface are basically the same. Okay? And I'm not going to do it because, again, I want to have more time for practice, so I'm not going to do the calculation right now, but I'm telling you now, if you put in G times the mass of the Earth divided by the radius of Earth squared, you should get 9.8. That's what you should get. Because remember, the force of gravity is the weight, and we know weight is mass, your mass, whatever it is, times G, M times G. So all this stuff turns into G for Earth, if you're on Earth. Okay, let's look at a second problem. Okay, practice number 2. So what I'll encourage you to do is pause, if you're watching the recording, pause it. And then if you're in class live, go ahead and try to calculate this one. This one's maybe a little easier. I don't know. It's the same, really. Okay, here is the answer I got. So again, just setting up the problem. F equals G, M1, M2 divided by R squared. G, same thing, times, pick one of the masses. Again, it doesn't matter which one is which, but 60 is one of the masses. Times the other mass is the moon's mass, divided by the distance squared. There's the distance between them. So again, just like calculator work, on top, I punched in, got 2.94 times 10 to the 14th. On the bottom, when I squared that, I got 1.47 times 10 to the 17th. Again, just be careful about using your parentheses and squaring. And then I got, for my final answer, 0.002 newtons, or 2 times 10 to the negative third newtons. Either way you want to look at that. So real quick, what does this mean? This is the, excuse me. This is the gravitational force that exists between you and the moon. Okay? It's not a lot. Moon is very far away, so it doesn't exert a lot of force on you. That is to say that you weigh 0.002 newtons less when the moon is above you, right? So think about, like, if it's a full moon and the moon's right above you, you would weigh that much less. Likewise, you'd weigh that much more when the moon is directly below you, so your weight can fluctuate. by the amount the moon there. Now that's not very much, obviously. 0.02 newtons is, let's see, go from newtons and we divide by the 9.8. That would be in kilograms. So multiply that by 2.2. That's about 0.0004489 pounds. We turn that into ounces, about 7 thousandths of an ounce. So again, a pretty negligible amount of force that exists between you and the moon. Okay, let's look at another one. This one is a little different though. We're looking for something else, right? So this time we're looking for a different thing. So let's look at that together. Let me pull up my copy of this. All right, here we go. So it says you're located on a foreign planet, so we don't know what planet this is, some other planet. And it says, you know, your mass is 80 kilograms, that the planet you're on has a radius of 4.8 times 10 to the 4th meters. You step on a scale which says that you weigh 478 newtons. Find the mass of the unknown planet. So this time we're not trying to find the gravitational force. We know the gravitational force is 478 newtons. And just to be clear, when we say weight and gravitational force, those are the exact same things. That is what the gravitational force means. So let's just write the equation first, and then I'll show you how I would approach this. The force of gravity is going to be obviously big G m1 m2 divided by r squared. So there are two ways you can do this. Number one, you can put numbers, substitute numbers into the equation, and you'll have everything except one of these masses. Let's just, for the sake of this, let's say that this is going to be m2, and that we're going to call the mass of the unknown planet, we're going to call it m1. Again, it doesn't matter if you switch those up, it won't make a difference. I just want to be consistent here when I'm talking about it. So you'll know all the numbers except m1, and then you can, algebraically move these things around till you get m1 by itself. So you can go ahead and multiply G times m2, you can do r squared, you can divide it and then do that. I think it's actually simpler just to solve it algebraically first and then put the numbers in, because then I don't have to worry about doing the numbers, calculating, and then moving things around. Again, it doesn't matter to me which method you want to use. All right, well, let's say I'm going to do it algebraically first. So I want to get m1 by itself. So what do I need to do to get m1 by itself? First thing I need to do is get rid of G and this m2, okay? Currently I'm multiplying, right? I'm taking m1, I'm multiplying it by G, and I'm multiplying by m2, right? So to get rid of those, I have to do the opposite. The opposite operation of multiplication is division. So I'm going to divide both sides by G and both sides by m2. So divide by G, divide by m2, divide by G, divide by m2. Okay, cancels, cancels. And over here, nothing cancels. Then I still have to get rid of this r squared. So right now I'm dividing by r squared. So the opposite of division is multiplication. So multiply both sides by r squared. And again, this side it cancels. This side it doesn't. So now I have this new equation, right? So I'm going to rewrite my equation. So on this side I just have m1 equals. On the other side, it doesn't matter what order you put these in. I'm just going to put f g first times r squared on top divided by G times m2 on bottom. Okay, hopefully that makes sense. Again, all I did was I just did the opposite functions of these to get rid of them on this side, and they went to this other side. Because again, in order for the equal sign to stay the same, I have to do the same thing to both sides. And this is my equation. Now again, you don't have to do it this way, but once you have this equation, that's it forever. I mean, like, since you can use your notes on the test, you could write this equation down and you have it forever. Like, you'll always have it. Okay, so then it's just calculator work. M1 equals. The Fg is the force of gravity, which we know is newtons, 478 newtons. So that would be 478 times the distance squared. So the distance here is this number here. That's the distance for the surface. So it's like from the surface to the center. So that's 4.8 times 10 to the 4th squared divided by G is 6.67 times 10 to the negative 11 times M2 was just 80. Okay, so again, just doing the calculator stuff. I'm going to do 4.8 times 10 to the fourth in parentheses squared, and then multiply that by 478. So on top of this, I get 1.1 times 10 to the 12th. On bottom, I did 6.67 times 10 to the negative 11 times 80. And I got a pretty small number. Let's see if I can get it in scientific mode. There we go. That's 5 times 10 to the negative 9th. Then I just divide. So again, I'm doing parentheses, 1.1 times 10 to the 12th, divided by parentheses 5 times 10 to the negative 9th. And for my answer, I get 2.2 times 10 to the 20th. This would be kilograms for our mass, M1. Okay, those are all the practice I have. I do want to show you one more thing, though, just so you see it, because I think there is a question like this. Okay, I just want to show you what it looks like if you solve for R, right? So let me rewrite the equation. F G equals big G M1 M2 divided by R squared. So what if I want to just solve for R? Like, let's say there's a problem where I knew I wanted a specific force, and I want to know how far away would I have to be to have that specific force, right? So let's say I knew the masses, I knew obviously G, and I knew the force, and I wanted to find R. So again, I would suggest solving it symbolically first. So if I was trying to get R squared by itself, the first thing I always do, if it's in the bottom, get it out of the denominator. So I multiply both sides by R squared. So that it would obviously cancel on this side, this little point. And then I would have just R squared. So then I would have F sub G R squared equals G M1 M2. And then if I want to get R by itself, let's get rid of FG first. So I divide both sides by FG. So it cancels here. I have R squared equals G M1 M2 over FG. Great, but I don't have R by itself. I just have R squared. So just like we did with Kepler's laws the other day, if I want to get rid of the square, I have to do the opposite function. The opposite function of a square is a square root. So I take the square root of both sides. And then I finally get this R equals the square root of G M1 M2 over the force. Okay, I wanted you to see that again. We're not going to do a specific problem with it right now, but I think there, if I remember correctly, there is one on the practice. Okay, so that's Newton's law of gravitation. I think it looks more complicated than it is. Really, it's just mostly identifying what pieces are which, and then putting into a calculator. You know, if you struggle putting in the calculator, then you know you can work on that, and I can help you if you need it. But as long as you can do that, it's really pretty straightforward.